Hello and welcome to my level maths practice videos. These questions are based on proof. The first question is write out the following sets as lists of elements. So we have even prime numbers. So even prime numbers, there's only one even prime number, and that is 2. The factors of 28, the factors of 28 are 1, 2, 3 is not a factor. We have 4 as a factor, no 5, no 6, and then 7. 4 times 7 is 28. And then we'll have 2 times 14 is 28 and 28 itself. The next one is x such that x square is equal to 1. So x could be minus 1 or plus 1. So that's going to be my set. So the next one is telling me disprove the following statements by giving a counter example. Okay, so we have to prove this is wrong, it's not correct. So if x by y is less than 1, then x is less than y for all values of x and y. So here we will assume that let x be equal to 1 and y equal to minus 4. Okay, then if x, then when we do x out of y is equal to 1 to minus 4, and that is less than 1, so this holds true, this part holds true. Okay, so now so x by y is less than 1, right? But however, you see that x is not less than y. However, x is greater than y, as 1 is greater than minus 4. Okay, so the statement does not hold true. So the statement is not true. Okay, so that's done. The next one is x squared plus y equals y squared plus x, then x equals y. So we can derive it from the statement itself. X squared plus y equals y squared plus x. So, or we can rewrite this, rearrange it by changing the sides, or we can write x squared minus y squared is x minus y, or x plus y, x minus y equals x minus y, or x equals minus y. So then it doesn't hold true, it's not. So the conclusion, so the second part of the statement, x equals y, is not true. So the statement is not true. Okay, so the statement is not true. Is that correct? Yeah. Now you can do this in another way as well. You can make some assumptions, like you can say that if x equal to, or you can say let x be equal to 0 and y equals 1, then we can say that 0 plus 1 equal to 1 plus 0 plus 1. Yeah, so x equals 1, then this is true. Okay, yeah, that is equal to 1 plus 0. But however, if you do as a minus 1, okay, then it doesn't hold true. If it's plus 1, it is true, but if you do it as minus 1, then you will get 0 minus 1 equals 1 plus 0. So which means minus 1 is not equal to plus 1. So the statement is not true. Okay, so you can prove it. So then the next question is, okay, this says prove that for any integer n plus 6 whole square minus n plus 1 whole square is always divisible by 5. So what do we have here? We will expand this, n plus 6 whole square minus n plus 1 whole square. If I expand this, equals n square plus 6 times 6 is 36 plus 2n, then minus n square minus 1 minus 2n. So n square goes, it's not 2, it's 12n. So we are left with 12n minus 2n is 10n minus or plus 35. Or if you take 5 out, you get 2n plus 7. Okay, which is a multiple of 5. So 5 times 2n plus 7 is a multiple of 5, because 5 times a numbered integer means it's a multiple of 5, right? Now they're saying, so this is always a 2n plus 7, or this is divisible by 5. So or we can say 5 statement holds true. Okay, so that way, yeah. I mean, then we can add another statement that 5 times an integer, any integer, is divisible by 5. Okay, so the statement is true, so this holds, right? So the next question is, prove that the difference between an integer and a square is always even. Okay, so this one we can do an integer. So for any integer n, the difference between an integer and its square, the between an integer and its square is written as n square minus n, that is n, you bring it out, n minus 1. Okay, so n minus 1 is odd. So if n is odd, now if n is odd, okay, this is a point to note. If n is odd, then n minus 1 is even. Okay, and when you have an odd multiplied by an even, you get an even. Any odd number multiplied by an even number, yeah, odd multiplied by even. Like for instance, if you take 6 multiplied by 3, you get 18, which is even. If you get 9 multiplied by 6, you get 54, which is even. If you do 9 multiplied by 2, is it 18? It is even. So odd multiplied by even equals even. Okay, so if n is odd, okay, is even, or what we get is n times n minus 1 is even. Okay, when n is odd. Okay, now if n is even, then n minus 1 is odd. or you can say is odd, or if n is even. So then again in this case what you get is even, because n is even, multiplied by odd, that would also be even, right? So odd multiplied by even is even, even multiplied by odd is even, you know. So n times n minus 1 is always going to be an odd and an even being multiplied together, and it is going to be even. So the statement is true. So the statement is true, okay, that the difference, okay. So okay, so as an extension we can write that since an integer has to be either odd or even, and in both cases, or in both instances, n times n minus 1 or n square minus n is even. So the difference between an integer and a square is always even. Okay, so the statement is true. Okay, so the next question is the following statement true or false? Give either a proof or a counterexample. Okay, so in this question what we have to do is we will expand the brackets, okay? So if we expand the brackets, we will get x plus 2 times x minus 1. So x plus 2 times x minus 1 is x squared minus 2x plus 2x minus 4. That's x squared minus 4. Okay. So that is, okay. And then if we, this is the, that is, if we say that's the left hand side, and 2x minus 2 equals to 2 times x minus 1. Okay, wait a second. No, I'll do it another way. Yeah, to do the whole thing together. So if I do the whole thing together, that would mean x squared minus x plus 2x minus 2 minus 2x. So our x squared minus x is greater than 0. Okay. So this means our x times x minus 1 is greater than 0, right? So that means our, if x times x minus, so then x minus 1 or x greater than 0, right? When x equal to 1, so we get that. Now what we can do is we have to do a proof or by counterexample. So now if we assume, right, now if x equals 1, then 1 times 1 minus 0 is 1. Okay, so Yeah, yeah. So this is not working, is it? Yeah, it's greater than 0 when x is 1. If we do x is 1, this is not greater than 0, this is 0. So this is not working because 1 minus 1 is 0, so this is not working. If x equals 1, then it is 1 times 1 minus 1 is 0. So this statement, x squared minus x is greater than 0, is not true. Okay, if x, for all values of x, if x equals minus 1, then minus 1 times minus 1 is equal to minus 1 times greater than 0. So then statement is true. So I think it's and what I'm trying to explain is if you have x equals 1, then 1 minus 1 is 0, not greater than 0, so the statement doesn't hold true. And if x is minus 1, then the statement is true, but then x squared minus x, or x times x minus 1 is 1, is yeah, is, what am I doing here, is 1, not what did I do here? So it's wait, just what, I'm writing too many minuses, and so this bit, what comes out is minus 1. You have minus 1 whole square minus minus 1, that is 1 plus 1 is 2, which is greater than 0. So the statement is true if x is minus 1, and statement is false if x is 1. So the statement is not true for all values of x. Okay, so the statement is false. Okay, it's not true in both cases. It's not true for all values of x. It's only true when x is 1. So it's not working, right? So we can say that it only works if x is 0 less than equals x. So in this range, the statement would work, would be greater than 0. Yeah, because if it is in this range, then it's in fact, yeah. So if we were to use a fraction, so if we were to use this one now, so if we said half whole square minus half, that would mean 1/4 minus half is minus half, isn't it? Which is not greater than 0, so it is less than 0. So it's not working again. This is wrong. So it doesn't work in these cases. The only part where it is working is if you have a minus 1. So if you had a minus half instead of this, it would be minus half whole square plus half, and that would give you 1/4 plus half, which is greater than 0. So it works only if it's less than 0. if x is less than 0. So if x has a negative value, it will work. Then for other values, it doesn't work. So I think we can say that it's not true. Okay. Is the statement true or false? So the statement is false. The question 3. That so we can say that the statement is false. Okay. So the next one, right? So this one, what we have to do is we have to prove by contradiction. Right, if x is irrational, then minus x is also irrational. So let us do this by so assume that this statement is not true. Then there is a rational number x for which then there is a rational number x for which minus x is irrational, not irrational, obviously. Minus x is rational. Okay, so what happens if x is rational? So x can be written as a by b, where b is not equal 0. Okay, and a by b, a and b are rational, and a and no, let's not write this, b are rational, right? So x can be written as a by b, where a by b is rational. Now minus x, if minus x is rational, and minus x can be written as minus a out of b, which is also rational, or you can say minus a, which is also rational. So the idea is if a by b is rational, then minus a by b will also be rational. Okay, so but this will contradict the statement that x is irrational. Okay, so assume the number x is, so this is irrational. There is an irrational number, so this, no, wait, I'm going to do this again. Let me do this thing again. So what we're trying to do is we're going to have an irrational number for which there exists a rational number with a negative sign. Okay, so that's what I'm trying to do in a very convoluted way. So then if assume that there is an irrational number, there is an irrational number x for which minus x, this is irrational, is rational. So if minus x is rational, so minus x can be written as minus a by b, where a, b are rational. Okay, so minus a by b is rational. If minus a by b is rational, or no, unknown zero, yeah, rational, and a and b is not equal to 0. Okay, so x equals minus a by b, which is also rational. Right? But this contradicts the statement that x is irrational. So here we said that x is irrational. So here we are saying that x is rational. So this contradicts the statement that x is irrational. Right? So then what we get is the statement is yeah. So if x is irrational, then minus x is also irrational. Or if x is rational, then minus x would also be rational. So it cannot have that the negative of a rational number is an irrational number. That is not possible. Okay, so that's what this thing is about. The next question is telling, so it says prove by contradiction. So there is no largest multiple of 21. So what I have to do, that there assume there's a largest multiple of 21, which is assume that is by contradiction there is a largest multiple of 21 which can be written as n. Okay, so because the multiple of 21 and equals 21n, because 20 is a multiple of 21, so where n is an integer, n is an integer. Okay, so what do we get now? If there is no largest, so if there is no, so assume there is a largest multiple. This is the largest multiple. So if n is the largest multiple, even then, because 21n is an integer, there is another number which is 21n plus 21. Now there can be a number 21n plus 21, you can add 21 to it, or n plus 21 which is larger than n. Okay, so yeah, so that's the n plus 21, or this, so there is, so which is larger than n. So if There means there is no largest multiple of 21. However large multiple is, there will always be a number which you can get by adding 21 to the largest multiple. So there is no largest multiple of n, because this is an integer. So which is also a multiple of 21. So there is no largest multiple of 21. So there is no largest multiple of 21. Okay, so hopefully, sorry, my writing is a bit, yeah, so that's, I think that does this. The next one is prove by contradiction there is no largest integer power of 10. So, and then there is no smallest integer power of 10. So that means you can have an integer n which is equal to 10 to the raised to the power 10 raised to 10, or 10 to the power 10. Okay, 10 to the power n, sorry, 10 to the power n. So there is no such largest integer power of 10. So n can be, there is no largest, n can be, go up to infinity, So that's here what we're trying to say, prove by contradiction that there is no largest integer power of 10. So how are we going to do this? So we assume that the largest integer power of 10, so for A we will assume that the largest integer power of 10 integer power of 10 can be is n, where n equals 10 to the power small n, where small n is an integer. Now if you multiply this by 10, if we multiply n by 10, we will get 10 to the power n times 10, multiplying both sides by 10, and 10 plus 1, so there's one power higher. Okay, and again if you multiply it one more time, you will get n 10 to the power n plus 2, so it's another power higher. So there is no largest power of 10. Okay, so then n, so then because I have to write it, so this contradicts the statement that n is the largest largest integer power of 10. Or not largest number, large number, because yeah. then n is the largest integer power of 10. Okay, so this is how it goes on. So this is done. The next one is saying prove by contradiction there is a smallest integer power of 10. So it is the same way we will be doing this. So we can easily write b here. It will follow the same routine. So all we have to do is, instead of largest, I can write smallest. Okay, and then instead of writing n multiplied by 10, I am going to write n divided by 10. So this will be divided by 10. So then it's going to be 10 to the power n minus 1. Okay, so then this contradicts the statement that n is the smallest integer power of 10. I think that's what it is. So there is no smallest integer power of 10, because if you divide, you will get 10 minus 1. Okay, so if you divide it one more time, you will get n to the power 10 raised to the power n minus 2. Okay, yeah. So there is no smaller number than n. So yeah. So then yeah. Smallest, so there is no smallest integer power of 10. Okay, next one is if p plus q is irrational, then at least one of p or q is irrational. Right, so here again, it's again the contradiction thing. So we have to assume that the statement is not true. Okay, so if the statement is not true, then there exists two rational numbers, p and q, such that then there are two rational numbers, p and q, such that p equals, no, rewrite p plus q is rational. Irrational, that would make it contradict, doesn't it? So there, yeah, so p plus q is irrational. So there are two rational numbers, p and q, such that p plus q is irrational. So if p and q are rational, then p equals a by b and q equals b out of c, where a, b, c, d are integers. Okay, b and c not equal 0. So integers. So if you do p plus q, you will get plus not B by C, C out of D plus C out of D, okay, and that will be AD plus BC by BD, which is also rational. Because BD is not equal 0, and this is also a rational number. Okay, so now this contradicts the statement that P plus Q is irrational. So this statement is being contradicted. So we can write this contradicts the statement that P plus Q is irrational and P plus Q cannot be irrational if both P and Q are rational. Okay, so if P and Q are irrational, at least one, either P or Q, have to be irrational. So if P plus Q is irrational, then either P or Q have to be irrational. Okay, so that's what we get. So either P or Q have to be irrational. So otherwise it doesn't work. Okay, so that completes our proof that if P plus Q is irrational, then at least one of P or Q is irrational. Because if P plus Q is rational, if P and Q are rational numbers, then P plus Q also will be rational numbers. The only way P plus Q can be irrational is when either P or Q is irrational. Okay, so that completes this. The next question is saying for any two prime numbers P and Q, where P greater than 2, Q greater than 2, prove by contradiction that PQ is always odd. Okay, so what do we do here? So suppose there exist two prime numbers, okay, P and Q. Okay, P greater than 2 and Q greater than 2, such that PQ is even. Okay, that is our start. So we are going to write, suppose there are two prime numbers P and Q such that P greater than 2, Q greater than 2, such that PQ is even. So PQ can be written as 2n. So PQ equals 2n, where n is an integer. Okay, so if PQ is 2n, then PQ is even. Multiple of 2, that's even. Okay, but then it is not, yeah. Now, but the thing is, so now the thing is, because they are prime, so we have to get back to factors. So then the factors, so the factors if they are prime, okay, so the factors of yeah, then let's write. So 2 is a factor, so the no, not the factors. So if I write 2 is a factor of PQ, okay, but P and Q are prime numbers individually, and so 2 cannot be a factor of P and Q when you multiply them, but P and Q are prime numbers, and okay, but P and Q are prime numbers, so the only factors are the number itself, 1 and the number itself. Okay, so they are the only two factors are. Okay, so if P and Q are prime numbers, so then if PQ equals 2n, then one of them has to be 2, or Q has to be equal to 2, because if P is 2 and Q is 3, then the product of two primes will be even because it's 2. However, then the product of if either of them is 2, then the product will be even. Okay, then the product will be even, because then if P is 2 and Q is 3, then PQ is 6, which is even. However, they have said it, and we have said it at the beginning, that P is greater than 2, Q is greater than 2. However, since P and Q are greater than 2, so PQ is always odd. However, since P is greater than 2 and Q is greater than 2, then the product PQ is always odd. Okay, it cannot be even, because it's only if they are 2, either one of them is 2, then it can be even, otherwise it will be odd. Okay, so I think that completes the session. This was the last question, the last of the proofs in this chapter. So I'll be back with more questions, more proofs, and more stuff from different books. And keep watching, and thank you for your time. Hope this helps. Any questions, do send me an email at mathsforeveryone@outlook.com, and thank you.